Hello everyone, we are going to present on the topic laser and its applications. First of all, let us see what is a laser. The word laser stands for light amplification by stimulated emission of radiation. It is one of the most significant inventions developed during the 20th century. In 1917, Albert Einstein first theorized about the process which makes lasers possible for stimulated emission. The laser beam was invented in 1960 by a physicist called Maiman. Lasers have found tremendous variety of uses in electronics, medicine, computer science, etc. A laser is a device which emits light through a process of optical amplification based on stimulated emission of electromagnetic radiation. It differs from other devices because of its property of coherence, which means all the waves have the same phase and frequency. Now let us see the properties of laser. The first property of a laser is monochromatic, which means it consists of a single color or wavelength. In ideal case, the laser emits all photons with the same energy and thus the wavelength is same. The light from a laser typically comes from one atomic transition with single precise wavelength. So the laser light has a single spectral color and is almost the purest monochromatic light available. The second property of laser is divergence and directionality. Laser beam is highly directional, which implies that laser light is of very small divergence. The directionality is described by light beam divergence angle. Divergence is more in ordinary light as compared to laser light. Due to divergence, the major application of laser light is used to measure the long distances such as distance between the moon and the earth. The third property of laser is coherence, which means that all the individual waves of light are moving precisely together through time and space. For any electromagnetic wave, there are two kinds of coherence, namely spatial coherence and temporal coherence. Correlation between the waves at one place at different times are called temporal coherence, and correlation between different places but not along the path is called spatial coherence. The fourth property of laser is brightness. The brightness of a light source is defined as the power emitted per unit surface area per unit solid angle. The maximum brightness is reached when the laser beam is perfect spatial coherent. Now let us see about the construction of a laser. A laser consists of a gain medium, a mechanism to supply energy to it, and something to provide optical feedback. In the figure we can see that the gain medium is the material with properties that allow light to amplify by stimulated emission. For a gain medium to amplify light, it has to be supplied with energy. This process is called pumping. The energy is typically supplied as an electrical current or as a light at different wavelength. Pump light may be provided by a flash lamp or by another laser. The most common type of laser uses feedback from an optical cavity which is designed to internally reflect IR or UV waves so they reinforce each other. The most common type of laser uses feedback from an optical cavity. There are two types of mirrors. One is partially reflective and other is totally reflective. Light bounces back and forth the mirror passing through the gain medium and amplified each time. Depending upon the design of the cavity, the light coming out the laser may spread out or form a narrow beam. This type of device is sometimes called a laser oscillator in analogy to electronic oscillators. Now let us see the principle of laser action. The principle of a laser is based on three separate features. stimulated absorption, spontaneous emission and stimulated emission, and population inversion of electrons. First of all, let us see stimulated absorption. It takes place if an electron is in the excited state with energy E2 and it spontaneously decays to the ground state, releasing the difference in the energy levels between the two states as photons. In the figure, we can see that stimulated absorption occurs when a photon strikes an atom with just exactly the proper energy to induce an electronic transition between two energy states. Spontaneous and stimulated emission. Spontaneous emission takes place when an electron in a higher energy level drops down to a lower energy level and a photon is emitted which is equal to the energy difference between the two levels. The phase and direction of the photon is completely random due to the uncertainty principle. Conversely, a photon with particular frequency would be absorbed by the electrons in the ground state. The electrons remain in the excited state for a period of time, typically less than 10 to the power minus 6 seconds. Then it returns to the ground state spontaneously by photon. These processes of absorption and spontaneous emission cannot give rise to amplification of light. So the best can be achieved. For every atom absorbed, another should be emitted. Stimulated emission. Stimulated emission takes place when a photon with an energy equal to the energy difference between the two levels interact with an electron in the higher level. Alternatively, if the excited state atom is perturbed by electric field of a photon with frequency, it may release photon of the same frequency, which is in phase with the first photon. Then the atom will again decay into the ground state and the process is known as stimulated emission. The emitted photon is identical to the stimulating photon with same frequency, polarization and direction of propagation. All of the three processes occur simultaneously within a medium. Now let us see about the population inversion. If the higher state has greater population than the lower energy state, then light in the system undergoes a net increase in intensity, and this is called population inversion. It is a necessary condition to sustain a laser beam, so that there are enough excited atoms that can be stimulated to emit more photons. To achieve non-equilibrium conditions, an indirect method of populating the excited state must be used, which is done using a 3-level laser and a 4-level laser. Now let us see what is a 3-level laser and a 4-level laser. A 3-level laser has 3 energy levels E1, E2 and E3 and populations N1, N2 and N3 as shown in the figure. The energies of each level are such that E1 is less than E3 less than E2 and the energy level 2 lies between the ground state and level 3. Here initially the system of atoms is at thermal equilibrium and the majority of atoms will be in the ground state. That is N1 will be equals to N2 and N2 and N3 will be equal to 0. Now the atoms are pumped from the ground state E1 to the higher state E3 with the help of pumping source. Here E3 is called the pumping state. The lifetime of atoms is least in the energy level E3, which means that E3 is unstable state. And here the atoms stay for 10 to the power minus 9 to 10 to the power minus 8 seconds. Then the atoms make transition from E3 to E2. So the energy level E2 is the metastable state, having lifetime of about 10 to the power minus 5 to 10 to the power minus 3 seconds. Thus population of atoms become more in E2 as compared to E1. The stimulated emission occurs between E2 and E1 producing laser. Here E2 is known as upper laser level and E1 is known as lower level laser. An example of a three-level laser is a ruby laser. There are some drawbacks of a three-level laser. In a three-level laser system, the terminal level is the ground level and hence more number of atoms are to be transferred to E2. So this requires more pumping power. Also, if the difference of the atoms in the two levels is small, the power required is also small. So the efficiency of a three-level laser is less. Now let us see something about a four-level laser. Here there are four energy levels E1, E2, E3 and E4 and the populations N1, N2, N3 and N4 respectively. In the figure we can see that E1 is less than E2, less than E3 and E4. Here the atoms from the ground state E1 are raised to the excited state E4 with the help of pumping. From E4, the atoms decay to the energy state E3 by spontaneous emission. The transition rate of atoms from E4 to E3 is much faster as compared to the transition rate of atoms from E3 to E2. This is due to the reason that E4 is an excited state with lifetime of atoms of order 10 to the power minus 8 seconds. E3 is a metastable state. Thus, the number of atoms in E3 exceeds the number of atoms in E2. The population inversion is achieved between E3 and E2. So, the lasing action takes place between E3 and E2 by stimulated emission. The atoms from energy state E2 get de-excited to E1 and the atoms from E1 are again pumped to E2. Also, there are some advantages of 4-level laser over 3-level laser. In case of 3-level laser, the lower state is the ground state. So, in order to depopulate it, a large amount of pump energy must be put so that the ground state is actually in lower concentration than the excited state. The only way to depopulate the ground state is to put in more and more pump energy. So, a 3-level laser requires more pump energy. But in case of a 4-level laser, only a modest pump energy may be efficient to establish a population inversion between states 3 and 4 if state 3 is metastable and state 4 is unstable.
Types of laser. The most important and known types of lasers are classified as solid state lasers, gas lasers, and semiconductor lasers. Now, solid state lasers. Ruby is an important solid state laser. Aluminum trioxide crystal is doped with chromium 3 positive ion impurity to obtain ruby rod. The ruby rod is placed in the glass tube as shown in the figure below. A xenon flash lamp is used as excitation source. The electrodes of the flash lamp is connected to a battery in parallel to a capacitor. This capacitor is used to supply short duration of high current pulse. As a result, the excitation is produced by the discharge of capacitor across the helical flash lamp surrounding the ruby rod. Photons generated in the active material undergo to and fro between the mirrors and hence simulated emission takes place through mirror 1. The figure shows the energy level diagram of a ruby laser. The pumping of the crystal is obtained by the intense light from the xenon flash lamp. It is a 3-level laser system since only 3 energy levels are involved in the process of simulated emission. The energy level is achieved up to 2 energy levels, that is E2 and E1 bands of chromium 3 positive ions. The ions then decay and goes to energy level M. M level acts as upper energy level. Transition takes place between E level and ground state, resulting in emission of photons. Now let us see the gas lasers. Gas lasers has a mixture of gases and their amplifying substance as their amplifying substance. It is cheaper than solid state lasers and yield highly coherent radiation. Helium and neon and carbon dioxide lasers are the most widely used gas lasers. The helium neon laser is an atomic laser. The active medium used in the helium-neon laser is a mixture of helium and neon gases in the ratio of 10:1. A current for radio frequency discharge is applied in the gas mixture. This discharging mechanism ionizes the gas mixture inside the glass tube. The figure shows the construction of a typical low-power helium-neon laser. A narrow diameter glass tube containing mixture of helium and neon gases of about 10 mm of mercury is used for excitation. Excitation takes place in the discharging tube. Applying a high DC voltage, about 2 to 4 kV, is applied from power supply for excitation in the discharge tube. The resistance limits the current after limitation of charge. This figure shows the energy level diagram relevant to the operation of helium-neon laser. Energy pumping is achieved by electron impact excitation of helium of atoms either to metastable state 2 to the power 1 S0 or 2 to the power 3 S1. The population inversion takes place from 3s to 2s to 2p energy levels. As a result, emission of light power occurs in the helium-neon laser. Figure also shows the helium-neon laser is a 4-level system. So the electrons must decay energy as fast as possible to reach the ground state in 2 steps. In the first step, the transition is rapid from 2p to 1s and then 1s to ground state slowly. The rate of transition in second step may be increased by collision with the wall of the discharge tube. Therefore, gate of the laser may be increased with the decrease in radius of the tube. Again, increase in population in 2p level causes decrease in population inversion. So output of the helium-neon laser cannot be inversed by increasing the input current only. Hence, helium-neon laser is a low-power device. The next is a carbon dioxide laser. It is a molecular gas discharge with laser action taking place in 2 vibrational levels of carbon dioxide gas. In this design, the gas is sealed in the glass tube. This laser configuration can be pumped either with DC or RF excitation methods. In DC excitation is used with a sealed tube carbon dioxide laser, then it must like construct as the helium-neon gas laser. However, it is necessary to have an elaborate cooling system with the laser. The energy is coupled to the laser using a matching transformer designed for the maximum power transfer. The output from the RF supply is applied to a number of electrons that are spaced around the laser gate. The RF energy is absorbed with very little temperature rise. The energy level and during the process shown, the lower lasing level must remain with the low population. Therefore, the molecule must be removed from the lower lasing level as soon as it has emitted its photon. This can be done by cooling the gas, but most cooling systems cannot cool the gas quick enough to keep the lower lasing level depopulated. Therefore, the helium gas is used in carbon dioxide lasers. When the helium gas enters the process, then it removes energy from the carbon dioxide molecule by atomic collision and so reducing the molecule to a lower energy state. Semiconductor lasers. It is the smallest of all types of lasers known. They have a size of a fraction of a millimeter. The laser consists of a semiconducting crystal such as gallium arsenide, EV, etc., with parallel faces at the ends to serve as partially reflective mirrors. When the P and N-type layers are formed in intimate contact, the interface becomes a PN junction. In the process of doping of electrons in the holes, recombination takes place leading to the emission of radiation. The laser action takes place along the line of the junction. Due to the polished ends of the block, the simulated emission goes in normal speed and a beam of coherent line is emitted from one of the two ends. Now let us look at the applications of the lasers. The scientific applications of lasers are spectroscopy, heat treatment, and lunar laser ranging. Now spectroscopy. As laser light is a monochromatic light with very well-defined range of wavelengths. So by careful design of laser components, the purity of laser light can be improved more than the purity of any light source. This makes the laser very useful source for spectroscopy. Number two, heat treatment. Heat treatment with lasers allows selective surface hardening against wear with a little or no distortion of the component. Because this eliminates much part of reducing that is currently done, the laser's capital cost is recovered in a short time. Lunar laser ranging. In lunar laser ranging, laser beams are focused into large telescopes on Earth aimed towards the Eris, and the time taken for the beam to be reflected back to the Earth measured to determine the distance between the Earth and the Moon with high accuracy. Now, medical applications of laser. Number one, laser eye surgery. Laser eye surgery or laser corneal surgery is a medical procedure that uses laser to reshape the surface of the eye. This is done to correct myopia and hypermetropia. And soft tissue surgery. In soft tissue laser surgery, interaction of laser light with the soft tissue provides a special approach to surgery. A highly focused laser beam vaporizes the soft tissue with a high water content. Number three is a military application. The first one is defensive countermeasures. Defensive countermeasure application can range from compact, low-power infrared countermeasures to high-power airborne laser systems. Higher countermeasure systems use lasers to confuse the seeker heads on heat-seeking anti-aircraft missiles. Number two, laser sight. The laser, as in most firearms, application is being used as a tool to enhance the targeting of other weapon systems. For example, a laser light is a small, usually visible light laser placed in the handgun or a rifle and aligned to emit the beam parallel to the barrel. Now, industrial and commercial applications. Number one, laser cutting. Laser cutting is a technology that uses a laser to cut materials and is typically used for industrial manufacturing application, but it is also starting to be used by schools, small business, and hobbies. Number two, laser welding. Laser beam welding, also known as LBW, is a welding technique used to join multiple pieces of a metal to the use of a laser. Now coming to the conclusions, a laser is a device that emits electromagnetic radiation through a process of optical amplification based on the simulated emission of photons. The wavelength of laser light is extremely pure when compared to the other sources of light, and all the photons that make up the laser beam have a fixed relationship with respect to one another. Laser is a powerful source of light having extraordinary properties which are not found in normal light source like tungsten lamps, mercury lamps, etc. The unique property of a laser is that its light waves travel very long distances and at very little divergence. Thank you.